That is the question. Okay, this seems to be the case that in roster notation this set can be written like this. But you must remember the point of using ellipsis. Ellipsis can only be used when there is a definite pattern that you can see the pattern, and from that pattern you can know what the ellipsis is hiding. In this case, what is the pattern? Is there any pattern? For example, what is telling me that these elements are in the set 1 by 6, 2 by 4, 5 by 233. These are definitely in the set. See, all of them are greater than 0 and they are less than 1. So they definitely belong to C. But they also don't have any pattern. They are not showing any pattern. For example, they are not telling me that 222 by 1, 2, 3, 4, 5 also belongs to C. Even if you write them here, okay, that is not a mistake, because these are elements in C. You can write them here, but even doing so will not tell you in any way that this element also belongs to C, because they are not following any pattern. The point here is that there are so many real numbers between 0 and 1 that no matter how many of them you write, you try to list, you will always miss something which is not apparent at all. And also one fact is that here the members or elements or numbers we have written so far, they are all fractions. That is, they are all rational numbers. But C has numbers which are not just rational. For example, nothing is telling me from this notation that 1 divided by root 2 is also an element in C. And this is not a fraction, although it looks like a fraction, but it is not a ratio of two integers. It's an irrational number, it's not a rational number, and still it belongs to C. Okay, so C is so large, C is far too large for roster notation. So this is where we need another notation or another method of specifying sets. So let's come to that. So this is called, the next one is called set builder notation or rule notation or rule method. So in set builder notation, what we do, we specify a given set using some objects and some properties that the objects are supposed to satisfy. Okay, it's best to describe with an example. Look at this set. Now I'm going to use set builder notation, so this is going to be something new, but I will explain that. What have I written here? It seems like a set in roster notation, but inside there are some symbols which are not quite known. What this says is that, okay, let me write the set in roster notation also. If you recall, by this symbol P, this slightly different sort of writing P, this is called blackboard bold. Okay, if you hold a chalk piece in a certain way and try to write these symbols, it will look like that. It is, if you recall, this is the set of all prime numbers. So in roster notation, we can write like this. Let me write several of them so that it becomes clear. Do you see that I am not leaving it with only two elements, 2, 3, and then I am using ellipsis? No, I have to make sure, I have to show that this is the set of all prime numbers. So 2, 3, 5, 7, 11, 13, 17, 19. So if someone sees this pattern, then immediately they will recognize that these are prime numbers. So P is the set of all prime numbers. So what the set builder notation says is that A is the set of all prime numbers small p. That means small p is an element of capital P. So what type of small p? Those p which are less than 10. Okay, so in set builder notation, what we do, we write a general element of the set. For example, this 2 or 3 or 5 or 7. These are p. And then we write, either we use colon or we use a vertical bar. And then we write the condition that this variable p has to satisfy. Here p has to be less than 10. So it means that A is the set of all prime numbers such that they are less than 10. This vertical bar or colon is, it means such that. So if I read it out, it sounds like this. A is the set of means these two brackets, those p belonging to capital P such that p is less than 10, or A is the set of those prime numbers that are less than 10, or A is the set of prime numbers such that the prime number is less than 10, and that there are 4 prime numbers less than 10, 2, 3, 5 and 7. So this is the set builder notation or rule notation. It has two parts. One of them shows you the variable, the general or the typical element of the set which is coming from some other set. Okay, and the second part shows the conditions. Here there is only one condition, there may be more than one, that the variable has to satisfy, and these two parts are separated by this vertical line or colon, not both of them together. Okay, either you write vertical bar or you write colon. Some people also write semicolon, but this I think is an old usage and they separate the two parts. Now, how can we write that previous set which we failed to write in roster notation in set builder notation? That is the real numbers lying between 0 and 1 that you may ask. So in set builder notation, we will just write like this. C, you recall that was the set C, is the set of real numbers such that R is a real number, and so in set builder notation you write the set C like this. Note that we are not listing elements, we are just saying what the elements are supposed to be. If we devise a special symbol for the set of real numbers like this, in fact this is the standard symbol, then we can write the set in a more compact manner like this. much like how we wrote that previous set involving prime numbers. Okay, so in set builder notation we can write like this. And in fact, while studying calculus, at one point we will study calculus, we will see that there are some even special notations for this type of sets. They are called intervals, and this is the closed interval 0, 1. But these things will come later. Okay, don't think about them right now. So in set builder notation we write like this. Set builder method or rule method. Now, what comes next? Okay. Now, if two sets are given, when do you say that they are equal? Obviously, they will be called equal if they consist of the same elements. That is, any element which is in one of them is in the other also, and vice versa. That is equality of sets. So, two sets A and B are said to be equal if they consist of precisely the same elements. And we write A equal to B. Okay, if they are equal, then we simply write A equal to B. If A and B are not equal, then we write A not equal to B. A is not equal to B. In this case, they do not consist of precisely the same elements. For example, 1, 2, 3. This set is equal to this set because order does not matter. So these two sets are equal. In fact, these two sets are also equal. Let us see if you can get this. Okay, the set on the left hand side, it consists of only one element, and that is the number 1. The set on the right, okay, this is in roster notation, but this is in set builder notation. So what the set builder notation says, this is the set of all real numbers x such that x has to be positive and its square has to be equal to 1. From elementary school level algebra, what you know is that there are two real numbers x whose square is equal to 1, and they are -1 and +1. But we need a real number which has to also be positive. Apart from being a number whose square is 1, it also has to be positive, and there is only one such number. So this set is nothing but this set. It has only one element. In spite of writing so many things, only one number satisfies all this, and that is number 1. So these two sets are equal. However, these two sets are not equal, clearly, because on the left hand side we don't have the element 3, so these two sets are different. So that is equality of sets. They are equal if and only if they consist of precisely the same elements. Now, after equality, the next thing we have is subset. A set A is said to be a subset of a set B if every element of A is also an element of B. Two sets are given, A and B. We say that A is a subset of B if every element of A is also an element of B. That is, if X belongs to A, then X also belongs to B. You see this, you recall from our videos on mathematical logic, this is an if-then statement. So it can also be written like this, or X belongs to A implies X belongs to B. So when this happens, we say that A is a subset of B, and we use the notation this or this to denote this fact that A is a subset of B. We can write like this also. This is somewhat like writing 1 is less than or equal to 2. 1 is less than or equal to 2, or 2 is greater than or equal to 1. When we first encounter set theory, it becomes somewhat difficult to remember these symbols. Okay, we already have come across this belongs to symbol, this relation. Then we have come across this subset. Now, how do we remember that something is a subset, A is a subset of B? One example I think will make it much more clear. You see, 1, 2, this set is a subset of 1, 2, 3. Why? You look at the definition. If there is an element in the first set, it also has to be in the second set. You go element wise. You first choose 1. It is in the first set.